Today we study X23Q, temperature and heat. So you can download this PDF file for the lecture from our KPOP digital library at kpop.org, and there's a table of contents. X series, you're looking for X23. We have a main textbook here, and you can click this to find
이번
the
시간은
lecture given in Korean, and click E to watch the lecture given in
from
English,
this class until the
and you can click this to return to the digital library, and you can click this to subscribe to the K-pop collaborations YouTube homepage. Okay, let's begin with X23Q, temperature and heat. Number one, we are considering the mixing the hot water and cold water, and we assume a hot water is at temperature T1 whose heat capacity is C1, and the other part has a heat capacity C2 at temperature T2. We assume that the system is closed so that energy is conserved. There is no energy loss or gain against the environment. Eventually, they arrive at the final temperature in equilibrium. So this problem can be solved by considering the energy conservation. The lost heat by the hot water is its heat capacity C1 multiplied by the temperature difference from the hot temperature to the final temperature, that is lower than the hot temperature. This amount of heat has been transferred to the other part that has a heat capacity C2. The temperature has been raised from the cold temperature T2 to the final one. We can solve this linear equation very simply, and we arrive at the final temperature. By the way, we are very familiar with this kind of mathematical object. We remember the center of mass of a system of particles, a two-body system, then the weighted average of the position vectors is nothing but the center of mass. If we restrict ourselves in one dimension, then simple replacement of these variables, temperature, heat capacities, and final temperature, they are the same as what we learned before to consider the Newton's laws of motion for a system of particles, especially two-body system. Then we remember there is a reduced mass defined by this formula, or the reduced mass is the product divided by the sum of the two masses. Why don't we construct a physical quantity that corresponds to this reduced mass in the two-body system? Then, just like the reduced mass, we can introduce the heat capacity, capital C, for something, And according to our solution of the final temperature, we pull out the common factor C1, C2 divided by the sum that is nothing but the C. And then the coefficient is replaced with the reciprocal of the other particle, the other part's heat capacity. All right, we arrived at the point. This formula, according to this, dividing both sides by C, we have this. Why don't we replace these variables with the kinematic variables of the two-body system? The T is to be replaced with the center of mass. C is replaced with reduced mass. T1 and T2 are replaced with the positions vectors in one dimension. And we find that these heat capacities are replaced with the mass of the other particles. We recall that the R, that is the relative coordinate vector, is defined by the displacement from particle 2 to particle 1. In here, in a thermodynamic case, we have the hot temperature subtracted by the low temperature. All right, we recall that the position vectors are expressed can be expressed in terms of the linear combination of the center of mass and relative coordinate vector. And the coefficient of the relative coordinate vector is the partial fraction of the other particle's mass relative to the total mass. And the signs are different because the center of mass is in the middle of the particles. And the ratio of distance ratio is reversed. Now we recall this formula that has been identified that we have proved already. Why don't we replace all of these variables with the thermodynamic variables? Because what our method to solve these linear equations are identical to each other, so just a simple replacement is enough, and we don't have to solve the problem once again. Finally, replacing x with temperature, replacing the center of mass with the final temperature, and replacing masses with the heat capacities, keeping the sign the same, and we arrive at these formulas. So I hope you can enjoy this kind of way. So when you study physics, you always remember what you have done with some mathematical structure, because in mathematics, they don't teach you in detail any aspect of change of uh, replacement of numbers with the physical variables. And in physics, it is very important to feel what's going on with the change in the variables of kinetic variables or thermodynamic variables that has a certain physical meaning. So during the time, you save a lot of time if you remember what we have done with a very similar mathematical, uh, different physics problem, but that has a identical mathematical structure. For example, you repeat solving quadratic equation you learned in middle school in many cases, just like that. You can reproduce those results, these tedious calculations, not by hand but by reduce or mathematica automatically. Next, we consider list of physical quantities that are not simply additive. Okay, why don't we mix two materials with different densities? So we have the definition of density rho, mass over volume. We mix up two matter And the final density is nothing but the sum of masses divided by sum of volumes. Okay, in that case, according to this definition and for each material, I can replace this one with mass with rho times rho 1, V1, rho 2, V2, V1 plus V2. What's that? This is identical to the previous structure. This, well, is it? This one and center of mass. The weighted average. Just, they all have a common structure of a weighted average. Okay? Please remember, please remember. These numbers are not to be added simply, but the, any kind of physical variable that is defined as a ratio of two physical variables, then you always have the similar structure of weighted averaging. This one also appears in computing the center of mass of system of particles, and we can find the center of mass of a system of particles. Why don't we consider a single system and the center of mass of another system of particles? And what happens if we mix them all together? We also have the same structure in it. Let's see. The center of mass of the whole system is, by definition, weighted average of every particle. Mass, position, plus mass, position for every particle that are in either set A or set B, divided by the M1, M2, M3, M4. What's that? The total mass of the whole system. By the way, we divide this into two pieces. And what's that? This is A times total mass of the system A. Okay, A times total mass of the system A. What's that? That is the product of the total mass of the system B multiplied by the position vector B. All right, what's that? This is nothing but the center of mass of two particles, and each particle represents the position of the particle is the same as the center of mass of the first system, and position of this particle is center of mass of this second system. So this one reveals that the recursive structure appears even if you add many more systems. So systematic computation is very easily achievable. Number 3, consider a system consisting of n particles at the center of mass frame. Remember, we are working on the center of mass frame, in which the center of mass is at the origin. Xi is the position of the ith particle, and we define the relative position vector of a particle relative to the center of mass. Because we have chosen the center of mass frame, this guy disappears. So relative coordinate vector is the same as it itself. All right. Which one is different from the others? The temperature of the system, wait a second, the total kinetic energy of the system well defined. The total kinetic energy of the system is defined like that. By the way, they look different. However, because we have chosen the system at xcm is 0, its velocity is also 0. So they are identical to each other and they are all the same. So what about this temperature of the system? Unfortunately, temperature and kinetic energy, they are proportional to each other. However, temperature has a unit of Kelvin, Kelvin, Kelvin. kinetic energy joule, they are different. They are different in units of Boltzmann constant. And we have to multiply additional pure number that will be determined in the next chapter. Or consider a system consisting of n particles at the center of mass frame in which the center of mass satisfies you. Okay, that's fine. Everything is the same. Explain how to compute the average kinetic energy of the particles. Okay, let's see. We take I, the identifier for the particles, from 1 to n. Xi is the position vector, and we introduce the center of mass. Relative to the center of mass, we have x bar, that is the position of a particle, relative displacement from the center of mass. Because of this identity, I can take the time derivative to find out the velocity. All right. And we recall that the center of mass is a weighted average of the position vectors with the weighting factor, the fraction of mass. And capital M is the total mass of the whole system. We can straightforwardly show that this, let's see, what's that? We subtract this. So, sum of mass multiplied by the position vector. What's that? This sum is nothing but the total mass multiplied by the center of mass because of this definition. And this one is already factored out as a center of mass. And the sum of mi is nothing but the total mass. So same thing subtracted by same thing. Oh, that's a zero. Because it's a zero, its time derivative is also zero. Next, we compute the total kinetic energy of the whole system. Total kinetic energy is this, and the velocity of each particle is expressed in like that. We can expand this. So we have a center of mass velocity squared, and the 2 times center of mass velocity, scalar product with the xi bar, that plus the velocity relative to the center of mass of the every particle is squared. We remember that this is exactly zero, so go away. So we are left with these two terms. The first one is nothing but the 1/2 capital M total mass multiplied by the velocity of the center of mass squared. This is called the translational kinetic energy that is identical to the kinetic energy of a single particle whose mass is the total mass of the system and whose velocity is the velocity of the center of mass. The remaining part is the relative kinetic energy that is measured at the center of mass frame. By the way, we have chosen the frame, the center of mass frame. In the center of mass frame, xcm is a zero, always. Therefore, this guy will be gone. The only part remains is this. In addition, this is a positive definite number. This one has the minimum value, greatest lower bound, that is a zero. Only if every particle stops. Every particle does not move at all to have the zero velocity. We define this one. This state is called that 0 Kelvin. It does not mean this energy equals 0 Kelvin, but temperature is 0 Kelvin. We will rescale this energy in units of the Boltzmann constant and some number we will study later. That's it for today. Thank you.